Everyone. So today we're going to be doing a design related problem. This one is designing a linked list. Doing this in Python. Let's just dive into it. Design your implementation of a linked list. You can choose to use a singly or doubly linked list. A node can have two attributes, right? Val and next, which we know. Val is the value of the current node. Next is a pointer to the next node. If you want to use a doubly linked list, you need one more attribute. And assume all nodes in the linked list are 0 indexed. Okay, so we're making this class here, my linked list. It initializes the object, gets the value of the index node in the linked list. If the index is invalid, return -1. Okay, that's good, important. I'm not copying and pasting like I usually do just because this one's kind of long. So we're just going to be really referencing this problem as we go in sections. All right. Okay, so next up we have added head. Add a node of value val before the first element of the linked list. Makes sense. After the insertion, the new node will be the first node of the linked list. Okay. You need to figure out how to do that. We're appending a node of value at the last element of the linked list. Then we have another one called add at index. Add a node of value before the index node in the linked list. If index equals the length of the linked list, the node will be appended to the end. Okay, this sounds a lot like add at tail, right? This case right here. So that's probably important. If the index is greater than the length, the node will not be inserted. And delete at index. Delete the index node in the linked list if the index is valid. Okay, so a lot is going on, right? Then they give us this example here of how they're going to call our class here. So they make a linked list and then they call all of these functions, right? To manipulate it, let's look at the constraints. Do not use a built-in linked list library, okay? Index is always going to be greater than 0, and the values will be less than or equal to 1,000. I'm sorry, index will always, greater than or equal to, I don't know if I said that. At most, 2,000 calls. Cool, okay. So why don't we start here? We definitely need some sort of node class, right? So I'm gonna just make a new class here and call it list node. Oops. And I'm doing this in Python. So dunder init self. We need a self.val is going to equal something, right? Not that. So let's go ahead and pass in some values. We want a value and we want a next, right? Pointer to next. So self.val will equal val. And let's say self.next will equal next. So what if we don't give a next, right? In that case, why don't we give this default argument of none? Do I want a list node? If I don't give a value, should it also be a base of none? Should it have a default value of none? Or should we just force it? No, let's just leave it to you must say a value. Otherwise, you can't make it. I think that makes sense to me, right? If you can't give a value, then you can't initiate an instance. All right, cool. So just keep formatting the same way. Okay, so we have my linked lists, right? So what do we have in linked list always? Let's go ahead and start writing some comments. So if I have a simple linked list here, right? BC, I'll do 3 nodes. I know that I want a head, right? We definitely need a head here. So let's just say this dot head, and if you create a linked list, well, if we initiate a class, if we initiate a linked list, do we want the head to actually equal anything in the beginning? Like for example, when I do this call, yeah, I don't think so, right? New my linked list. So let's just go ahead and call this none. And do you need anything else here? I don't think that's it. Yeah, I think that's it. We just need a head, right? Head, and we have our value in our next mechanism on the list node. So I think that's it for now. So okay, get. Let's go back up. Why don't we do this in the order of how we would actually build it, right? So if we have a linked list here, I think that makes more sense. And let's say right here, right? You call my linked list add at head. All right, great. So added head gets a value, and we want that to be the first node, right? So already when I was reading this problem, I saw that we're going to make an add at index function here. I'm going to reuse as much code as I can because there's no reason in rewriting it. So if I do an add at head, to me that's the same thing as add at index where index is 0, right? So I'm going to go ahead and just say self.add at index, and let's do a 0, and let's give it val. Right? We know that add at head does not return anything, right? Right here, there's no return value before the first element of the linked list, and after the insertion, the new node will be the first node of the linked list. Okay, cool. So yeah, we know that there's no return value, and it doesn't look like there's any other base cases that we really need to be aware of right now. So if we were to draw this out, I call added head. Let's say I give it a value, right? Oh, I'm sorry, yeah, added index 0 and val. So yeah, that's it for this. So let's go ahead and think about how we're going to build this here, right? If index is 0, meaning, so first I know the value coming in. I need to definitely make a new node, right? So let's call this new node. I think that works. And I want this to be the new head, right? So that means that when index is 0, we basically want to replace whatever is currently at this dot head, right? So this is a special case though because we're actually replacing the head, right? So if index is 0, let's say we should be copying this head, right? Why? Because, well, we're going to reassign this head to new node, right? And then I'm also going to, or actually, instead of using a temporary node, we could just say new node.next should be equal to this dot head, right? and then this dot head becomes the new node. Perfect. Okay, so does this work? Well, think about it. New node dot next will become this dot head. Well, head is currently none. That's fine. And then this dot head becomes the new node. So now in our example, that our fake example, this one, right? Added head 1. So right now we have a linked list with just 1. Cool. And I'm going to return because this is a special case and I definitely don't want to do any more code in this function. So let's just return it here. Okay. Cool. So now let's see. What's the next one? Added tail. Okay, cool. I want to add at tail 3. So added tail 3 is we want this to look like this, right? But right now we just have 1. Okay. So let's say self.add at index, right? Because I said I want to reuse it. And okay, well I know I'm definitely using val, right? But this value here, the index, well I don't know what I don't know the length of the linked list, right? So okay, I need to find the length of the linked list. Now I already have a feeling that I'm going to need to find the length of the linked list in other functions, right? Like, for example, right off the bat, I'm thinking of when they said, right here, added index, if the index is greater than the length, the node will not be inserted, right? So in this function that we're building, I still don't have that logic. But if I have a way to check the length, then we can build this logic, right? Same thing goes for added tail. If I can check the length quickly, I can... Oh, wait a minute. Oh yeah, I'm sorry. Not yeah. If I can check the length quickly, I know where to assign this index, right? So let's go ahead and I'm just going to go ahead and build a new function, which is get length. And let's do this get length, returning an int, right? It's always going to be a whole number, so it's not a problem. All right, what's a quick way to find the length of a linked list? I'm already thinking of using recursion, but right off the bat, I know if I do recursion, space complexity will be O of n for the call stack, right? Which we want to avoid if we can. So I'm going to use this using an iterative approach. So I'm just going to say cur. I'm going to copy the head. I'm going to say while cur equals cur.next, right? And then I'm just going to have some sort of count starting at 0. And each time I move to the next node, I'm going to increment my count. And perfect. So at the end of this, I just need to return count. Right? Easy. If you don't know how to do this, check out some of my other videos. I believe in Leetcode 75. If I have not uploaded that yet, there is a way. There's a video in regards to, or there's a lot of videos on how to iterate through linked lists. So check that section out on my website. Okay, so let's go back to where we were. So we're going to add an index. All right, cool. So I want to add a value at tail. So I definitely need to find the length first, right? Definitely need to find the length first. Okay, so this will give us the length. Let's just call this the current length, right? Always good to use very, very clear variables. If it's not clear to you, it's not clear to your interviewer, so be careful with that. And let's think about this, right? So what is the current length of our linked list? It's 1, right? Now we want to add at index. What index? Well, right now I'm going to write the indexes on the bottom, right? The top represents the node, bottom represents the index, like that. So I basically want to add a node at 1, right? Which is the length of the list. So we could just pass this current length, right? That makes sense to me. Boom. Bada bing, bada boom. Okay. Adding at index. And now let's account for this one, this case, right? So if we like the actual logic, which is going to go into adding this next node here, right? So if we call added index on 1 and the value, what was it, 3, right? Because we called added tail, that calls added index. So how can we accomplish this? Well, add at index 1. First, I know that I need to get to this node, right? And then when I get to this node, I need to do some logic, which will basically assign this next to whatever new node we are giving it, right? So we know that we have a new node here, but we need to get there, right? So why don't we say cur equals this dot head, similar to how we iterated right here, right? Cur equals this dot head, while cur equals cur dot next. However, we also need to account for index, right? So right here, add index is 1. So it bypasses this section. Then this says while cur. So cur is currently at 0, right? We're currently at the head. And we have index equaling 1. So cur now equals cur.next. So makes sense to me. Why don't we just go ahead and take index and minus 1 from it, right? That way, we can basically iterate this forward, right? Sorry. So then let's think about this a little bit deeper, right? We are right now iterating through the entire linked list. But what this problem is asking is, or I'm sorry, what this function is asking us to do is add a node at a certain index. So that's the same thing as asking, well, if it starts off at 1 and we're decrementing our index by 1, then we can actually say while cur and index is greater than 0, right? Because once index hits 0, we know we are at our final, we're at our destination, wherever we want to insert, basically, right? So at this point, if you think about it, cur should be equal to the index at which we want to insert, right? In other words, cur. So let's think about our current example. Well, actually, our current example is a bad one because we handled 0 as a base case, right? If the index is 0. Oh, wait a minute. I'm sorry. Index is not 0. Index is 1. So while cur, so it's 1, and the index is greater than 0. So it's 1, and then we go to the next one, so now it becomes none. Now it becomes none. No, then it's way too far ahead. I forgot something. I think we need previous, right? So we'll start previous off as none, and then previous will be actually equal to cur. So let's redraw this out, right? You're going to have, on the very first instance, we have a C. C stands for current, and then we'll have P pointing to none, right? So this is just off to the side here, not pointing to anything. So index is 0, and then it iterates to the next. So now C points to none, right? This is a none right here. And then now previous points to 1. Yeah. And so now we can say, okay, previous equals cur, current equals current.next, decrement index, while current and index is greater than 0. So actually both of these conditions end up being false right now, right? So it jumps out of the loop, and at this point you can just say previous.next should equal new node, right? Why? Well, think about it. This is previous right here, points to this node, and then we're saying we want to add a new node, so previous.next. So the new node we're adding is 3, right? And take note that C, or current, was pointing to none, right? Current equals current.next. So you should also write in cur.next, or I'm sorry, new node, right? We added in new node. So we want new node.next to point to current. Now, right now in this specific situation, this line doesn't matter because current is pointing to none, and we, as we know, when we instantiated, new node, this node is already pointing to none, right? So this is kind of useless right now. The reason why I did this is because, remember, this function adds at any index, right? Not just the last one. So, for example, if we had a longer list like this, and let's say I wanted to insert something here, previous.next should be 4, current points to none, right? Before we add the 4 in, current points to none. So previous.next is now 4, but I need 3, I'm sorry, I need this new node. Oh, I'm mixing myself up here. So this is what I was meant to do. Okay. If you want to add a node in between, right, where it's this is 1, this is 2. Yeah, okay. So previous.next needs to point to this new node. So let's say we add in like something like 6, right? Current is pointing to 5 at this point. So previous.next becomes 6, So now new node 6 needs to point its next to 5. Yes. Right. And so that is why I'm adding this line here. Yes. So, okay, so far this looks good to me. Sorry, I'm confusing myself a little bit here, but just doing this as I go. So let's revert back to how our list looks at this point. So now we know our length is 2 because we added 3 to the tail. And why don't we also, so add a node value val before the index. If index equals the length of the list node, the node will be appended to the end of the linked list. Okay, so we've accounted for that, right? If the index ever equals the length of the linked list, which is essentially add a tail, append the node to the end of the linked list. So that's done. That's this, right? And we've also taken care of if we want to add a node in between, this should also work, right? However, what we did not account for yet in this is if the index is greater than the length, the node will not be inserted. Well, that's a case that we have not considered yet. So why don't we go ahead and do that? So we have, as we already have a get length, right? So if get length, don't forget self if you're using Python, if self.getLength, which is the length, is actually if the index is greater than this, then we already know that this is not a valid index. So we can actually just return, right? That should handle that case. Cool. Okay. What else are we missing here? So I skipped get. Let's see. If the index is invalid, return -1. Okay. So why don't we account for this first, right? If the index is invalid, that means that the index is negative, right? No such thing as a negative index if we're doing a singly linked list right now. So if the index is less than 0, right? Or also if the index is greater or equal, right, to self.getLength. So why equal? Well, think about it, right? If you have right now the length is 2, there is no node at index 2, right? So that doesn't make sense. So it says if that is so, return -1. Okay, cool. So now how do we get the node that we want? Well, similar to how we iterated on the bottom, we can just say while cur equals just a head. Just a head. And we'll say while cur. Actually, while index is greater than 0. I'm going to say cur equals cur.next. And then that way, once we jump out of this loop, cur should equal what we want, and we can just return current.val. So why can I do this? Because, well, we already check whether or not index is greater than or equal to the length. So we will never run into a case where cur is going to point to none, right? We are guaranteeing with this base case here that this is possible. Actually, if we go back to this, I think we can apply the same logic here because can we? Or maybe we can't. Nope. Because cur will be none if it's at the end. Like if we are adding something to the end of the linked list, current will definitely be none. But is that an issue? I actually don't think that's an issue because we also have checking here if the index is ever greater than the length, meaning even though current equals none at the end, it won't run this for the last occurrence. So I don't think we'll ever be reassigning, we'll never hit this part basically, right? So I think we can remove this too. I'm going to remove it for now, but just write a note that I took out cur in case we run into some issues later. All right, cool. This looks looking good. Okay, delete the index node in the linked list if the index is valid. Okay, sounds like once again self.getLength, right? If the index is greater than getLength or equal to, or equal to, because it must be in the linked list, right? So if it's the length, it's not valid, and if it's greater than the length, it's not valid. So we can just return. And we can also say if the index is less than 0, meaning it's negative, we can also return. That's not possible. All right, cool. So, oh, I forgot that we are following this. So let's just quickly add these in. So add at index 1, 2. All right, I'm going to walk through what I have right now. So add at index, it makes a new node of 2. If the index is greater than self.getLength. Self.getLength is currently 2. So we have the index of 1. Is index greater than 2? No, right? So we go to the next part. Is index 0? No. So we go to the next part. So current equals 1, right? This dot head. Previous equals none. Okay, so let me just write this out. Previous. Previous. And this is current. Perfect. So while the index is greater than 0, so the index is currently 1. So now previous becomes current. And current becomes current.next. And we minus 1. So 1 minus 1. Now index is 0. So we stop. Right? And we say, okay, exactly what I have out. Previous.next. So previous's next becomes the new node, which we saw was 2. Okay, cool. 2. Previous's next becomes 2. And remember, current is still 3. I'm going to move that over. So now it says that current, I'm sorry, here, new node dot next, previous is, oh, no, new node, this is 2. So let's write n here. New nodes dot next becomes current, which is 3. Yep, that looks right to me. Cool, so this is a straight current state of our linked list. So now it says get 1. Okay, get 1. If the index is out of bounds, right? So it's asking us to get the index at 1. So index is not, 1 is not less than 0, and what's length? Length is currently 3. Forgot to update that. So 1 is not greater than or equal to 3. So we skip this. Current equals this head. All right, let's go ahead and erase these pointers. Current is 1. So while the index is greater than 0, well, the index is 1. Current equals current.next. Oh, looks like I caught a bug. We forgot to minus index by 1. So now 1 minus 1 becomes 0. Current points to 2. Return current.value should be 2. That is correcto. Now, alright, perfect. Delete at index 1. So we want to delete the index of 2. How can we achieve this? So we already checked the bounds. That's good. So if we want to delete at index 1, well, same thing here, right? We need to first get to the index, right? So while the index is greater than 0, and if we're doing a delete, I already have a feeling that you need a previous and a current. Right, so I'm going to say previous starts at none. I'm going to say current is this head. Why? Because, well, when we're deleting a node, we're essentially taking the previous and assigning its next to something else, right? You're assigning its next to current.next. That's how you delete the node. You just change the pointers, right? We're not actually deleting the node from memory. We're just reassigning pointers of the linked list. So while the index is greater than 0, we know that we have to decrement, right? And I know that I'm definitely going to be iterating. Reassigning current to current.next. And similar to this pattern up here, we should also be saying previous will equal current. Alright, so now we can say something like, so now current is equal to the node that we want to get rid of, right? And previous points to the node before it. So let's think about this. How do we delete, let's say, in this example, we want to delete this one. So previous would point to 1, current would point to 2. How can we delete this node? Well, we can basically say previous dot next. I want to assign that to 3, right? Current dot next. So previous dot next will equal current dot next. Like that, right? And that would essentially just get rid of that. Like that. Now this becomes 2. Now quickly, let's think of other base cases for this one, right? What if the index is, I think there's 2 things we would have to consider. So if I just draw a quick one like this, if I want to delete the node in the front, basically what happens is this becomes the head, right? So that's a special case that currently this would not work, right? Because while index points is greater than 0, this would never run, and then this would call none.next, which I already know is going to error out in Python. Alright, so I'm going to say if the index is 0, right, there's a special case we need to consider. So let's just say this dot head equals this dot head dot next, and then we can return. That's a special case. Another special case, what happens if it's at the end? How can I delete a node at the end? So why is this cannot? Did I not do that right? I'll figure that out later. How can I delete it at the end? So if we're at the end of the linked list, so 0, 1, 2, so this is 2, right? So once this goes all the way down to 0, current will be 3, and previous will be 2, and previous.next, I want to assign it to current.next. Current.next is currently none. So previous.next, actually, we've already counted for that. Yeah. So we took care of that already, right? Because you see, previous.next is going to point to current.next, which is none. So that would just cancel that one out. That one's good. Cool. So, okay, we consider the base cases if it's at the front or if it's at the back. And then in the middle here, we have a get length here. Am I missing anything here? We could consider the front. Do we consider the end if we want to add at the end? I believe so. I think that was the first thing that we did, right? So, previous.next equals new node.next will equal cur. Then you add a tail. That looks good to me. So yeah, let's run through the last one here. You get 1. You should just get 3. So, okay, we have 1 here, length of 2. That looks accurate. So is 1 greater than 2? No. So while the index is greater than 0, current equals current.next, so index, so this becomes cur, and then you have 1 minus, so it becomes 0, and then you just return current.val. Yeah, that looks good to me. Let's quickly talk time and space complexities, right? So I think it's worth doing it for all of them just to see, like, is there anything that we can optimize? So I know this, let's say n is the number of nodes in our linked list. While index is 0 or greater than 0, so this is definitely O of n, right? To get a node, we have to walk through the whole linked list. Added head and added tail. Okay, this is O of n, right? To get lengths. O of n. Added head and added tail are dependent on the time complexities for this. So time complexities, same thing. Get length here. This is O of n. This constant. This is O of n. We also took out cur, but not important right now. But that's O of n. Same thing right here, right? O of n. O of n. Oops. Oh, that's even better. O of nodes. This is O of n. This is also O of n, which I already wrote down. Cool. So that looks right to me. I don't really think you can get quicker than O of n for any of these because adding at tail, adding at index, adding at head. Well, actually, this would be always O of 1, right? This is an O of 1 operation. But like adding at a tail, unless we kept track of the tail, I guess that could optimize. If we kept track of the tail on every single operation and stored the tail as a pointer, then I guess we could get this down to O of 1. I'm not going to write that out right now. I don't really think that's super necessary, but that is an optimization I can think of. Getting always sounds like n, right? No matter what. Yeah, like unless you were somehow constantly keeping track of the indices of each value, I'm sorry, of the each node in some like array kind of structure where you could easily, I guess you could bring this down to O of 1 if you were somehow keeping track of the indices. So basically like having a array, list kind of structure that is keeping track of each single node. Actually, it couldn't be an array though, because once you add or delete, that will mess up. That will make add at index much. Actually, that will. I wonder if that's what they want us to do though. So actually, you know what? Let me just run this right now, see if we're passing. And then we can optimize it more if we want. But this should work for now. Let's see. This is not defined. Oh gosh. This is because I have been working with students in JavaScript. One second. Self dot head. Is that right? Self dot head. Yes. So okay, try. Cool. Pass the case. Let's submit. Okay. Line none type has no attribute next. 66. What did I mess up here? None type has no attribute next. Previous x equals current next. So let's see here. If I think it has to do with deleting at the last. So if we want to delete at the last one, it's going to be 0, 1, and 2, right? So we want to delete at index 2. So we skip this, and you say previous equals none, and current equals self.head. Then you keep going. So 2, the index is currently 2. So previous, okay, we go 1. So now index is 1. Previous index is 0. So now it jumps out. And then it says previous.next. Choose next should point to none. No, so it's not that one. Delete at index. Well, if index is the first one, if it's the beginning, we're handling it. If it's out of bounds, unless my bounds are wrong. No. None type has no attribute next. So that means that could this ever be none dot next? Let's say it's 1. What if it's 1? So previous becomes current. Current becomes current dot next. Index is -1 becomes 0. Then it jumps out. No, that's also not possible. Oh, I see. Wait a minute. My linked list, we added head, so now it's 2, and we're deleting at the index of 1. So index is less than 0. It's not. The index is 1. Oh, if the index is less than 0 or I think that's it. Yep. Hot dogs. Small case. Cool. Okay, so back to what I was discussing. This video is quite long. I know that we can probably optimize some of these things, but I want to see if it's even necessary. Yeah, so right here, O of 1 for added head and added tail. So this is using a doubly linked list, but let me see here. O for 1 for added head, O of k for get. Let's go back to, so since we used a singly linked list, I'm going to see if we're hitting these benchmarks. So, what just happened? I don't know what just happened. Hold on. So, okay, O of 1 for added head. So added head is literally this. So that's O of 1. Great. So that's good. Okay. O of k for get. I'm assuming k means some other variable that could be less than n. Let me just see how they did this here. Get the value if the index is invalid. Yeah, so it did the same way that we did. Increment to the value and then return. Cool. Okay. So that's right. O of k. I guess you could technically call this k, but I would still say n because at most, right, if you're getting the last node, it would be at most n. Not sure why they said k, honestly. where k is an index of the element to get, add, or delete. Yeah, I mean, I would still call that n because worst case scenario, you are getting the last one, right? Adding at index or deleting at index, the time complexity is still what we said before, right? O of n at most. And then O of n, okay, it's a strict n for adding at the tail. Okay, so I guess they didn't even, maybe my theory is not correct, but I think it is because yeah, if we always kept a running every single operation, we always kept a running track of where the tail is, or like the last load in the last node in the list, then that will make that operation O of 1, right? If you want to delete it, or actually not delete, if you want to get the tail, it's O of 1. If you wanted to add to the tail, like after, that would become O of 1. But very subtle, yeah, subtle things. O of 1 for all operations in terms of space. I'm pretty sure that goes for our solution here as well, because we're not using any space. But yeah, so here is the final solution. And I hope you enjoyed that. That was a long one, but definitely a good one to do. Something I also noticed is you probably could extract this. This looks like we're repeating a lot, right? You could technically make a function which helps you iterate to whichever index you want, and then I guess would return like previous or current and current from the function. That's something you could do, but you're not really going to get any time complexity improvements from that. It's just more of like a design, like not repeating code kind of aspect. I guess you could have also made this its own, right? Checking if something is in bounds. That could have been a function. Yeah, other than that, hope you enjoyed it.